Okay, guys. So, first thing for this problem is you want to be able to identify the equation you're going to want to use. Go all the way down the hallway. There should be one around there somewhere. Okay, so if you guys remember, there is a pH equation for buffers, and it's going to be this one right here. It might be in your notes. It better be in your notes, and it's also on your AP equation sheet. But this is the equation that we use to calculate the pH of a buffer. Okay, it's going to be pKa plus the log of the anion divided by the acid. Okay. Now, the cool thing about this problem is you barely do any math, but we just use this equation in order to kind of come up with the best choice out of these four, okay? All right, now before we even start, we can already get rid of some of the options, okay? Because if you guys remember, we have a buffer, right? And what is a buffer made out of? Yeah, you got to add weak acid, and you got its salt, okay? So just by looking at that, we can figure out that some of these are not buffers, or one of them is not a buffer, okay? So out of these three, okay, we can see that this one right here is not going to be a buffer, right? Because if you look at it, it looks kind of like a buffer because it has the same base right here, right? And by base, I don't mean base. It has the same like structure. But if you look at it, there is a HCl. There's a hydrogen and a chlorine here, not hydrochloric acid, right? And so these are actually not a weak acid and it's salt. So automatically you can figure out that D is not the right answer because this is not a buffer, okay? Just make sure that you're careful. I know that it's really hard to kind of see it, especially there's so much text. And so the way that I actually solved this was I just wrote the two reactants together next to each other just so I can see it a little bit better. But I don't know, maybe you guys can see it better because sight is not my strength. But just doing this for all four of them, that allowed me to see automatically, hey, even though these kind of look the same, this is not a buffer because it's not a weak acid and it's salt, okay? Does that make sense? Yeah. Okay. Alrighty, so we can automatically get rid of option D, so we don't need to worry about that. Okay, so we got these three right here. Now, we have to take a look at this equation now to kind of understand a couple things about this. Now, what we want to figure out is, or what we need to calculate, and this is the only calculation that you need to do. You should be able to notice that in order to find the pH of a buffer, we're going to want the pKa, right? And so let's calculate the pKa for both of these, okay? So I'll give you guys about a minute. I want you guys to real quick find the pKa of these two compounds, okay? Take a minute to find the pKa. So the pKa of this first one right here will be about 3.3. This guy right here will be about 10.6. Something like that. All right. Okay, so by taking a look at these, we can take a look at the pKa and we should be able to identify or notice that this value right here is very similar to pH, right? Now, if these two values are similar, what that means is it means that the pH will be equal to pKa when this ratio is the same. Makes sense? Because the log of 1 is 0. So pH is going to be equal to pKa when the concentration of your anion or the salt is going to be equal to the concentration of the acid. Does that make sense? That should be the first observation that you got to make. So like I said, this is kind of a hard problem. There's a lot of little things that you kind of need to identify, but just keep that in mind, okay? Bless you. Okay. Now, there is one more thing that you don't really need, but it might be a little helpful in different problems. If you guys take a look at the pKa of the other acid, the other compound right here, it's 10.6, right? Okay, one other thing that might be helpful in a different problem would be if you calculate the KB, the PKB, it's going to be about 3.4. Okay, because it'll be 14 minus 10.6. So the conclusion that we can draw from that is the buffer, so the acid in the buffer is going to be one of two compounds. It's either going to be this compound right here, HC2H4O2, or it's going to be the conjugate base of the other compound. Yeah, I'm just going to write other. Okay, so you can automatically figure out that the acid in the buffer is going to be this or the conjugate base. So you add a hydrogen, right? 2 plus. Okay, or the conjugate base of the other compound. Okay, it's not that one, but it might be helpful in a different problem. Okay, not on your test, but AP test or whatever. Practice problem 2. Other of the other one. So it's going to be either this chemical right here or the conjugate base of this guy. Okay, so far so good. Okay, I know it's a lot of stuff we're kind of putting together here. Like I told you, I try to find the hardest ones I can find. Okay, so let's go through the options now and figure out which of these mixtures is going to be our the buffer that has a pH of 3. Okay, we're gonna be looking for something where this gonna equal to that. Okay. Okay, so let's take a look at the first option. So here we have, if you look at it, you have a common ion, or sorry, not that one. You have a common ion right here that's bonded to Cl. Okay, so this is going to be your salt, and this is going to be your base. Okay, now if you guys write the reaction for this right here, we can kind of figure out that this one is not going to work because you write the reaction. Yeah, it's going to be NaCl, so that's going to be one of the salt, and then you're also going to replace. You're going to put the OH on this one, so it'll be CH3, CH2, NH3, and OH. Okay, so this isn't going to really work because these are your two salts, and then you're going to end up making a base, and then you got your strong base right here. So this isn't a very good option. Okay. Because again, you're looking for the acid because that's the pKa that you're working for. Does that make sense? Yes.
Why wouldn't they donate an H and H2O?
An H and a H2O.
Why does it accept the OH? Why doesn't it get the H? Why doesn't that get the H?
Oh, why doesn't it accept the OH? Or why does it accept the OH? Yeah, because this is going to be a strong base, and this is going to be a salt. You can tell because this is your cation, right? And this is going to be your anion, Cl. And then it's going to, because Cl is the conjugate base of HCl, it's going to want to turn to NaCl, which is aqueous, which will be Na plus and Cl minus. That makes sense. So yeah, this Cl is just going to want to dissociate because it's the conjugate base of a strong acid. Does that make sense? Yeah. Okay. So if you got that, this option is not going to work. Okay, so now you're left with two options. Okay. So between these two, if you guys notice, the big difference that you have now is going to be one of them is 100 mils of what type of compound is this? Not a salt. Yeah, this is a weak acid. Yeah, because it has H, right? And then this isn't one of the strong acids you have to memorize. So this is going to be your weak acid. And if you guys notice, that's one of the conclusions that we drew, right? That this could be an option in this buffer. And then you have 50 mils of a strong base. Yeah. Okay. All right. And then you got this option right here where, again, NaOH was strong base. And then what type of compound is this right here?
That is a salt.
Yeah, this is a salt. Yeah, because you got Na and then you have some kind of anion right there, okay? Which is same anion as right here. So this is also not going to work because you got a salt and that. So your answer is going to be B. Another reason why this won't work is because the 100 and the 100, if you have both of those, they'll cancel each other out basically. They'll neutralize it. Whereas here, if you write this equation, let me write it right here, just so that we have it. Let me go over this to answer your question. Okay, so for B, if you write the equation, you have HC2H4O2. You're reacting it with NaOH. If you guys look, H and OH, you're going to make water, and you're going to make your salt. Okay. And then if you notice, you had 100 mils of 0.1 right here. So this right here, you're going to be working with 0.01 moles. This will be 0.005 moles. And so this is going to end up canceling out 0.05 moles from here. So you'll end up with 0.05 moles of your acid left over. So that would be what goes right here on the bottom. And then you're going to produce 0.005 moles of your salt. And that's the value that goes up here. So this will cancel out with this. So log of 1 will be 0. And then pH will be equal to pK. And so that's the answer right there, B. So yeah, a lot of different steps in there. We're kind of taking like everything that we got. There's a lot of math in there, but that's how we get B. Okay. There are other ways to find the answer. If you wanted to go into each of the options, calculate the moles, see how they cancel out, that would have worked too. But that's kind of the easiest way to find the answer in my opinion. Yeah.
But how I'm kind of opposite.
Mhm.
C has an A, but would that automatically make it non-option as like the other one that I see now?
Yeah. If you know, yeah, that's another way to think about it. If you look at C, you got two sodiums on the, you got two compounds that have sodium on the reactant side. So you got your sodium and sodium, and so they're not really going to have much of a reaction. You'll have two anions which won't react. So yeah, that's another way to think about it to eliminate C.
Yeah, because in order to find the buffer, doesn't it have to equivalent to like the which they're getting it?
Yeah, you got to find, it's got to produce water and a salt. Yeah. So if you look at C, it's NaC2H4O2 reacting with NaOH. And if you try to do it, you got two NAs, right? So then for the net, these two aren't really doing anything. They're just going to dissociate. And then you're just going to have these two left over, and they're not going to react with one another because they're both anions. Okay. Yeah.
So it says that like, but it's showing like A and versus
Mhm.
But so it's like an acid association. Why do we find what?
You don't have to. Yeah. What do you mean conjugate? What conjugate do we find?
I don't know. You said we were like looking for the like.
We're trying to find out what the buffer is made out of. You mean that? Do you mean that part where we were figuring out?
Were you looking for a base like?
Oh, that one was for this one. If you find the pKb, it's going to be close to 3 as well. So that was another option. You could have had a buffer that's either contains this as your acid, or the conjugate base of this guy could also have been the acid in your. Yeah. Or it would be the conjugate acid, but yeah. Anything else? It's kind of a tricky one. There's a lot of weird moving parts in there. Did I demoralize you guys already?
Yeah.
Yeah, the point of finding pKa was to identify that because if you calculate the pKa, right, you wanted to identify that it was close to 3 because we're basing our assumptions based on this formula right here, right? The one that we had the pH for a buffer. So we found pKa because if pKa is very close to the pH, we can use this ratio right here to identify that if the top and the bottom are the same, that will be the log of 1, right? Because it'll be top divided by bottom. And then log of 1 is 0. And so the reason why we found pK was to figure out that we need equal concentration of salt and the acid role in order to find the pKa. And that's why B was the best answer, because we're left with the same quantity. So
Aren't all answers 0.1?
it is 0.1 molarity, but if you look, the volumes are all different. And so the volumes are what's going to prevent it. So if you, here, let me go back to this one. So if you take a look at this, we got our acid, we got our base, okay, and it's going to produce H2O and your salt, right? NaC2H4O2. Okay, and this right here is the concentration right here. And then this right here is the concentration of that. And so we basically needed to find which one of these mixtures is going to end up with this concentration, the equilibrium concentration of that equals this concentration right there. And this is the only one that's going to work. These other ones don't work. 100, 100, they'll cancel each other out. So you won't have any acid remaining. Does that make sense? Yeah. So the pKa was to identify this equivalence right here, that they need to cancel each other out. Okay. Any other questions? You guys ready for another one? Yes, I saw the light just disappear from your eyes as we did this problem. Okay, go. Okay, go donate blood. All right, let's do number 2. Number 2 is a lot easier, and I will start you guys off, and I want to see if you guys can figure this out on your own, okay? Okay, so we have the solution of a salt of a weak acid. The weak acid is Hz. It's a generic equation. It's added to a solution of another weak acid, which is Ha. Okay, and based on this reaction right here, we're basically trying to figure out which one of these compounds is the strongest base. Okay, and the key that they give us, or the big hint that they give us, is K is greater than 1. Okay, so if K is greater than 1, which side is going to dominate? Reactant or product side? Yeah, products dominate, okay? Okay, so we're going to say products dominate. Okay, if products dominate the reaction or the equilibrium, which side is the strongest base going to be? It's going to be on the left side, okay? Because the strongest, right, stronger acids and bases want to dissociate, or they don't want to exist, basically, right? They want to get rid of themselves. They want to produce their conjugates, okay? So the strongest base has to be on the reactant side, okay? And this makes sense because we talked about how HCl, it wants to break up, right? So it's going to push everything to the right side. We got a strong base like NaOH, it wants to dissociate, so it's going to push everything to the right side. So the strongest base is going to want to push everything to the other side, right? So if it's on the reactant side, it's going to push everything to the products. So the strongest base is going to be on the reactant side. So that's kind of where I'm going to help you guys out up until. And then so that kind of cuts down your choices to 2. And so try to take the most educated guess, or try to justify your answer for which of the 2 compounds on the right side are going to be your strongest base, okay? So try that out. I'll give you guys about a minute and a half to do that, and then we'll go over the end. Okay, so which one of these is the strongest base?
D.
Yes, D. Z minus is going to be the strongest base. Okay, so I helped you guys with the biggest part, but I think this is pretty manageable for you guys. If you guys thought about it, you guys could probably figure this out. And again, easy peasy. This one's the base because if you look at it, it accepts, it accepts an H+, so H+ acceptor. So this is your base. That means this is your acid. So this will be here, will be your conjugate acid, and then your conjugate base. A lot of information that you didn't need to write down, but just to help you guys understand, this is your base. Yes?
Can you explain again why the strongest base is going to be on the reactant side of the
Yeah, so let's look at some of the strong bases and acids we talked about, and just to kind of show the point. So NaOH is an example of a strong base, right? NaOH wants to break apart completely, right? So if we had this reaction for a strong base, one of the strongest bases, right? Which side is the reaction going to exist on? Which side is going to dominate, left or right?
The right side.
Yeah, the right side, right?
It's a strong one.
Exactly. Now, let's say we reverse the equation. Let's say this is our reaction. Okay. Okay, NaOH is on this side. Which side is it going to want to go towards?
Left.
The left, right? And it's going to be because this is a strong acid. So it's going to want to push to the left. Now, same concept here. We identified that K is greater than 1. We know that K is equal to the concentration of the products divided by the concentration of the reactants, right? Okay, and if you notice, K is bigger than 1, so what has to be bigger, numerator or denominator? Yeah, the numerator, right? This has to be bigger, which is the product side. So there needs to be more products, which is why we assume that products dominate. And because products dominate between these two, 1 and 2, which reaction seems the most similar to what we have here? It's going to be 1, right? And so that's why the strongest base has to be on the left side. Does that make sense? Yeah. I skipped a couple steps with the math, but that's kind of the reasoning. Okay, let's move on to 3. This one's a lot better, right? The number 1. Kind of want to crush your souls. What do you mean? Probably a combination. I probably won't put something like 1 though. 1 is like, this is kind of a really unfair problem.
Will that be on the something similar? No.
Not that hard.
Okay.
I can promise you. I don't know what's going to be on the AP
Oh,
test.
so as 2 on our test, or?
Yeah, something like 2 would probably be a standard MCQ question.
Okay.
Yeah.
On the AP test, will we get easy questions like that?
I don't know. I wish I can write the AP test because I would just mess with everybody and put the hardest problems. But okay, let's go to another problem about buffers. Okay, this one's a little bit tricky, and I'm gonna give you guys some time to work on this on your own, just to think out the parts, derive what you can from the problem. So I'll give you guys about 3 minutes to work on number 3. See if you can figure out what's going on and see if you can make the most educated guess. Yeah. This right here,
Yeah.
sodium lactate. Yes.
Okay.
Yes. Anything that has an alkali metal is a strong electrolyte, so the Na will break off. Yeah. Okay, guys. So for this one, I think personally the easiest way to do this is to figure out what the reaction is. Okay. So let's start with the reaction. So we're gonna take lactic acid, and then if you guys notice, you have the salt that corresponds with it, right? With the shared ion. Okay. And then you're adding NaOH to it. Okay, so let's say that we have our like a little solution, right? I'm gonna draw like a little beaker. Okay, and in the beaker we have this and this. Now, if you take a look at lactic acid, what type of acid is this? Yeah, this one's weak. Okay, and then you have your salt. Now, if you take a look at the salt, is it a strong electrolyte or a weak electrolyte? It's strong. It's Na. Anything that has Na attached to it is a strong electrolyte, which means this guy is going to want to break up completely into the cation and the anion. Okay, so it's going to break apart completely. So you can basically ignore the Na for the rest of the problem because Na is not going to completely dissociate no matter what. Thank you. Oh, you're going to go now? Oh, wait, this to pick someone up?
Yeah.
Okay, I can't read those. What the heck? If you can read that for me, I'll give you an A on the next test.
Sorry.
That does not say Jade. Okay? That does not. All right. That's literally like a scribble. All right. Anyway, so Na is not really important for the reactant. So let's take a look at the problem. So we have our weak acid. Okay, we have our weak lactic acid. It's going to be reacting with the strong acid NaOH. But again, we said we can ignore Na, right? Because NaOH is also going to dissociate completely. So we can basically ignore this. I'll see it. And this is going to be OH minus no. Or if you earn it. Okay, does that make sense? This is the reaction that's happening. We're reacting the weak acid with the strong base. And we can ignore the Na because strong electrolyte breaks apart. Okay, so if this reaction takes place, it's a neutralization reaction. You're going to produce water. And then you're going to have your anion kind of floating around. Okay, so far so good, guys? Okay. Now, we can do a fancy schmancy ice table to kind of just figure out what's going on in this problem. No. Well, you don't have to, but this is how I did it. Yeah, again, there's multiple ways to figure all this out. I'm just showing you the way I do it. but I have a sick, twisted brain, so might not be the best way to do it. I am suffering. Okay, so we have our ice table, and we can ignore the waters. Okay, so I'm gonna give you guys the calculations for moles because this is all in molarity, and we're gonna want to convert it to moles. So in the beginning of our solution, before we added the sodium hydroxide, you can take these values to calculate the moles of lactic acid. You should get 0.01. Okay, and before you add NaOH, you're not going to have any significant hydroxide floating around. And then you're going to have some of this, right? And this is going to come from your sodium lactate. So we can use these values to figure out how much sodium lactate is floating around. And that's also going to be 0.01. And this is all in moles, guys. Make sense so far? Okay. Now, for the change, let's talk about what was added. We added 5 mils of a 0.1 molarity NaOH. And so we're going to be adding 0.0005 moles of OH minus. So far, so good? Now, this came from a strong base, right? And so it's gonna, even though we're adding it, are we gonna have some OH minus at the very end? No, it is not. We are not. Okay, so it's gonna be 0. And you can justify this by saying it's a strong base. Okay, however, this is gonna allow us to calculate the change, right, between all of these. It's gonna be the same because the 1-to-1 ratio. So you're gonna lose some lactic acid, and then you're going to gain some of the lactate. Yeah. Okay. So if you get the numbers, basically the key here is that this is going to decrease and this is going to increase. Does that make sense so far, guys? Yes. That's the moles of NaOH that you added. You take the 5 mils, yeah. No, you're good. Yeah, please double check with me, guys. I know there's a lot of numbers and weird like things in here. So yeah, thanks for checking. But yeah, this is the moles of base that you added. I'll clarify. Okay, and so we're actually done. We can basically figure out the answer from here. So the question is asking, the first thing the question is asking is, which compound is going to be present in greater concentration? Basically, which one do you have more of? Do you have more lactic acid or the salt? Yeah, the salt, right? The anion, because you can just tell by the numbers, right? The base reacted with the acid to produce more of this. So that means A and B are automatically out of there. Okay? Now, you could do the calculation to find the exact pH, but let's just think about this logically. We added a base, right? If you add a base to something, it's going to become a little more basic, right? No matter what, even if it's a buffer. So if it becomes a little more basic, will the pH go up or will it go down? It'll go up. Bases are higher numbers. You're good. Okay, so it'll go up, and so your answer will be D, because lactic acid 3.9 is going to go up a little bit, so it'll be a little greater than 3.9. If you wanted to do the real calculation, you can do pH equals pKa plus the log of this. You can use this equation, right? You could plug this into the bottom, this into the top, find the log, pKa, whatever, but
it's like 3.9.
yeah, it's like 3.94. Yeah, so barely changed.
So I got these, but I didn't do any of that. I just like thought about it. Did I get one here? Like, it's just like NaOH is gonna like make one more base.
Yeah.
And then pH is gonna go. Like I just thought.
Yeah, so that works too. Yeah, if you can just kind of see, I guess the quick thought pattern will be, oh, the base is gonna react with the acid, so you're gonna lose some acid, so you're probably gonna lose some of this, so you'll have more of that. The key thing I would warn you though, if you do it like that, is make sure you know the reason this works is because you start with the same moles of acid and your salt in there. And that's the reason why that reasoning would work. Let's say that I had more acid or more salt, then depending on how the numbers work out, it might not work. Okay. But if they're the same amount, then yeah, if you added the base, then you would obviously use the acid to create the salt. Okay, does that answer your question? Yeah.
Sorry, can you refresh my brain, how you got 0.01 or I got point greater?
Yeah, the molarity equation is moles divided by liters. We'll do this one because they're kind of the same. Got 50 milliliters, you divide it by 1,000, you should get 0.05 liters. Okay, so you put 0.05 on the bottom. That's equal to molarity, which is 0.2. I'll just replace the numbers. Okay, and then you just do 0.2 times 0.05, and that'll give you 0.01. Yeah.
What you say we can do with the.
That if you add the base, that we can assume that it's going to react with the acid, right? So if you have the same amount of acid and your salt, if you add base, it's going to react with the acid, right? And so it's going to decrease your acid, increase your salt. Yeah, that's how buffers work. So, but you can only make that assumption for sure if you have the same acid and base. Okay. All right, not too bad, right, guys? One's okay? Okay. All right, let's move on to the next one, number 4. Oh, this one is not too bad, but it is a little bit tricky. So you guys, I think it'll be really easy to come down to 2 answers, and then you really got to think about which one's the right answer. So I'll give you guys about 3 minutes to do this one. Some of you guys might be able to get it like that. Other people might come down to 2 answers and think about it. But take about 3 minutes to try to figure this out. Work with the person next to you, and we'll go over it in 3 minutes. Alrighty, guys, we're gonna go over this problem, but because I was accused of dilly-dallying, let me tell you guys a story of my childhood. When I was a young boy, I was very fat and short. I really was. Okay, anyway. Okay, so this problem, guys, let's go over it. So we got a solution that contains HBr. Okay, what type of acid is HBr? Yeah, it's strong. Okay. And then we have HBrO2, and they actually try to help you in this problem by saying that this guy is weak. Oh, so weak. Right? And then they don't say anything about HBr, so you can already kind of see in the problem, hey, they're trying to tell me one's weak, one is strong, right? Okay, so we know that if you add, or in the problem it says that if they add enough KOH, in order to increase the pH to 11, right? So if the pH is 11, is this what type of solution is acidic, basic, or neutral? Basic. So basic. So basic. Okay, where's Uggs? Gets the, what do they get? Like the green tea frap at Starbucks. So basic, right? Wow. Oh, green tea latte, thank you.
So basic.
So basic. I do. I go to the mall, I walk around, I see a basic girl, I'm like to my wife, she's so pH 12. And she's like, what are you talking about?
It's like 14.
14, wow, off the charts. Okay, anyway. So if you add KOH to your solution, right? You got HBr and BrO2, and so you're gonna be adding H+. Or sorry, you're gonna be adding KOH. And the question is asking, which of these ion species is going to increase? Now, you can get rid of 2 of them right away. Okay, what's the first one you can get rid of if it gets more basic? H+. Obviously, this cannot work because if it's basic, you're not going to have H+ just floating around, right? The OH is going to gobble them up. Okay, what's the other one we can automatically get rid of? Ooh, HBrO2. Okay, never mind. Maybe it wasn't obvious. So if you take a look at this, this is not an ion. This is your weak acid, right? So if you add more KOH, what's it going to do with the weak acid? Neutralize it. So this guy, the concentration is going to decrease. So you're left with 2 species. And this one you might be like, oh, like which one is it going to be? Because if you add KOH to this, it's going to produce water, and it's going to produce K+ and Br-, right? That's the thought process. And this one right here, if you add KOH, it's going to produce H2O, and it's going to produce K+ and BrO2-, right? Okay, so we're kind of stuck, but you guys got to remember that one is strong, one is weak. Okay, So even before we added K plus, what does HBr do? It dissociates on its own. So it is already at the maximum concentration of Br minus. Br minus is already the max, all of it is just chilling by itself. This guy is single and he is sad. Okay, nobody wants him. Okay, because the conjugate base of a weak acid cannot get in a relationship. Okay, so we are already at the max amount of Br minus. And so this is where you kind of got to keep in mind where the strong and the weak acids differ, because even though we write the reaction like this, we got to remember that Br minus, since it's it's part of a strong acid, it already is broken up. And so no matter how much KOH you add to it, the amount of Br minus, the concentration of Br minus is going to be constant. Okay. Yeah, Br minus stays the same because even before I add NaOH, so let's say there's no Na or KOH in here.
Yeah, that makes
Yeah.
sense. It stays apart and they're not gonna
Exactly.
turn it in.
Yeah, so if I add KOH in here, KOH is only gonna react with this. This guy just kind of chills because, you know, in the reaction, we say it's gonna turn to KBr, but we know that that's a strong electrolyte, so they don't really form. They just kind of stay ionized. And so the only thing that's going to increase is this, because remember, this is a weak acid. Not all of this broke up yet, right? So the more base we use, it's going to push equilibrium to the right. And so the concentration of this guy is going to go up. So your answer is C. Yes.
So in the solution, like some of it's still together and some of it's like apart, so KBr, like some of it's still together.
KBr. KBrO2 or HBr? Yes, because it's the weak acid.
And then you add the base.
Yeah, it's gonna help it dissociate. Yeah.
Recently, the pages like here to start that HBr2, that like there's a little bit of BrO2 at the start. It's weak acid, it's at equilibrium a bit.
Yes. Yeah. Yep. Make sense?
That makes a lot.
I'm glad. Yes, let's take our 5-minute break. Yeah, for the 1 minute, you guys can be on your break, but I'll keep talking. Okay, so you can listen to my amazing voice. Okay, so we got this problem right here.
This isn't a break.
Too bad. So we got two acids. They're listed in the table below. Okay, and then you got 20 mils of a 0.1 solution each acid, and it's titrated to the equivalence point of 20 mils. Okay, so basically what this problem is saying is you're doing a titration problem and you have two different acids. Okay, so we'll call this acid number 1. We'll call this acid number 2. Again, we'll go based on the numbers right here. Okay, and it's basically telling us that both of these guys, both of these guys are 20 mils. Okay, and they're both 0.1 molarity. Okay, and their titration equivalence point is both 20 mils with the base that's described. So this guy, in order to get to the equivalence point, so 20 mils, 0.1 molarity NaOH, this is what it needs to get to equivalence point. And this is also what it needs to get to equivalence point. Okay. Okay, and equivalence point, if you guys forgot, is going to be where pH is equal to 7. Basically, you have the same number of your acid, same moles of your acid and your base. Okay, where they're equal. Okay, so it tells us the Ka values for these two acids, and based on the Ka values, we can actually go through the options and get rid of a bunch of different things. Okay, so let's take a look at the Ka values. Which acid is stronger, 1 or 2? Show me with your fingers. Show me with your fingers. Yeah, peace. Peace. Okay, yeah, 2 is stronger. Okay, so that's a bad color for that background. Sorry. No, def not yellow. Because it doesn't show up very well on the screen. If I can't see it on the screen. Anyway, this one is stronger. Okay, so let's take a look at the options. Now, if you look at the options, you'll notice that some of the justifications are factually incorrect, right? So if you take a look at A, it says blah, 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 because solution A is stronger. So you're like, this one is fake. Okay, you look at the next one. Same thing. This one also does not work. Oh, wait, sorry, stronger base, conjugate base. My bad. Acid. This one doesn't work. Sorry. Okay, sorry about that. So far, so good. A and C are out because they make factually incorrect statements. Solution A, this acid right here is not a stronger acid. Okay. B and D, they have the correct statements because they say that has a stronger conjugate base, which makes sense because, you know, it's opposites. This one is a weaker acid, so the conjugate base will be stronger. So now we just need to assess the other statement, the difference in these two statements, okay? The difference is it says in B that solution 1 has a higher pH at equivalence point, and this right here says has a lower pH at equivalence point, okay? So just by taking a look at the Ka values, we can figure out which one has a higher or lower pH. So if we take a look at solution 1, we said this is a weaker acid, right? If it's a weaker acid, does it have a higher pH or a lower pH? Higher pH. So there you go. It's going to be B. Okay. Yes. Yeah, so its pH is 7 when it's neutralized, but remember that titration curve? So there's going to be a little bit of a difference even when they're both at equivalence point. Yeah. Just because they have a different Ka value, it's going to dissociate a little bit more even when they're equal. And so it's still going to want to break apart. It's going to be a very minute difference. And that's why we have that chart. It's gradual for all of them. Yeah. Yeah, this one, the best way is just to kind of go through the options, eliminate the ones that don't make sense and pick the right one. Yeah. I don't think it's the best worded problem, but you can kind of find out the answer by getting rid of the options. Yeah. Because it's a stronger, or sorry, it's a weaker acid. Solution 1 is a weaker acid. Weaker acids have higher pHs. It's just the way the scale works. Yeah. Okay. That's good. So good. Wow. Ready to move on? All right, let's go to 6. Okay, 6. So 6 and 7, I'm just gonna go over them because there is some material that we didn't spend a lot of time on. I want to just make sure that you guys get it. Okay. Okay, so I'm gonna go through the question. It basically tells you that you're adding, yeah, you're gonna prepare a solution by adding HCOOH to NaCOOH. Now, if you guys notice, you should be able to see that this is going to be a buffer because you got your acid, right? And you got your salt, corresponding salt right there. And then the solution pH is 3.75. Okay, you're going to add, so you made your solution, and then you're going to add 3 drops, so very little amount of 1 molarity HCl. And the pH of the solution is still the same. So you're going to add a little bit of HCl, and the solution pH is still going to stay the same. Okay, basically it's asking out of these 4 reactions, why does it stay the same? Which one of these 4 reactions will justify the pH not changing, even though you added some acid? Okay, so we for this one, we have to go through every single one of them. Okay, so the easiest, or let's just go through them one at a time. The easiest one I think still to get rid of is the first one. If you take a look at this reaction, this one is actually a special one. It has a name. Does anyone remember the name of this reaction?
Self-ionization.
Yeah, self-ionization or auto-ionization of water. Okay. Okay. Now, just knowing that this is how what water does by itself, and water is neutral, we know that this isn't going to have anything to do with the pH not changing, right? Because you're adding an acid to it. Okay. Let's go to B. Anyone want to take a look at it and tell me what they think is wrong with B? There's 2 things you could say.
HCl is a product.
HCl is a product. Why can HCl not be a product?
Strong acid.
Strong acid, yeah. You're not going to want to reform a strong acid. Okay, so right here, the reason why this doesn't work is HCl is a strong acid. Okay, but it's on the product side. Okay, make sense? Okay, so A and B are not good options. Okay, so you're really going to be comparing C and D here. Does anybody want to try coming up with an explanation. Yeah, 우거지어낸 수열. C. So you think C is the correct answer?
Yeah.
Okay, why is C the correct answer?
The NIO
Uh-huh.
and the other one, yeah. It's
It's a what?
an acid on the.
Yes, that's correct. That's the reasoning. Yeah.
Yeah.
That's the reasoning why. So yeah, the answer is C. Very simple way that I like to think of it. That does work too. Is that if you take a look at D, right? If there is no detectable change in pH, that means you're still gonna require an acid on the other side of the reaction. So if you take a look at C, you have an acid in H3O plus, and you have an acid right here, right? So you got an acid and an acid. So you have 1-to-1 mole ratio. You have one acid molecule on one side, one acid molecule on the other side, right? So there's no real net change in the acidity. But if you take a look at D, you got one acid right there. Do you have an acid on the other side? Nope. So no acid. So it means you lost, right? You dropped an acid. So this one would actually increase the pH a little. So this one is incorrect. But your reasoning works. Other reasoning can work too. But that's just kind of way I think about it. Yeah.
These, like a hydrogen might disappear. It's 3 H's and 2 H's on that one, and it comes with 1 H.
3, 4, 5, 1. Yeah, so it's not balanced, but you would have to balance it out. Yeah. All right. Any questions? Okay, so this one is just literally process of elimination. All right, let's go to 7. 7, we barely touched this, but I'll tell you guys the answer just right off the top, and I'll explain why. The answer is going to be B. Okay, so it says, it's basically asking why is the pH of water at 37 degrees Celsius 6.8? Okay, so we know that the pH of, we usually say pH of water is 7. Okay, but that's under the assumption that temperature is at what temperature? 25 degrees Celsius. Okay, but this problem is saying, hey, at a different temperature, the pH of water is 6.8. So the temperature of water is 37 degrees Celsius. Now, you can just memorize this if you want, but as temperature decreases, water is going to get slightly more acidic. Okay. Sorry, thank you. Temperature increases, water is going to get a little more acidic. Now, I'll tell you the reasoning why. We didn't go over this reaction in class, and that's why I'm kind of just briefly going over this. But when you take a look at, yes. Thank you. Okay, when you guys take a look at the equation of the auto-ionization of water. So water, even though it's just chilling by itself, it's auto-ionizing, right? So if I have a water molecule and it's auto-ionizing between, H plus and OH minus, or you could think of it as 2 water molecules, H3O plus and whatever, you can do that as well. Now, this reaction right here is going to be endothermic, okay? This is an endothermic reaction, okay? Just a observation that we made in experimentation, okay? So if it's endothermic, is energy a reactant or is it a product? It's a reactant. You need energy, I'll see it. Okay, you need energy for this reaction to happen. So if I increase the temperature, are you adding reactant or product?
Yeah.
You're adding reactant because you're adding energy, right? You're giving more energy to the molecule. So if we remember Chandelier's principle, which way does it swing the reaction?
Right.
Yeah, to the right. That'll increase H plus. I'll see it.
So that one's for if the temperature decreases.
Yeah, temperature decrease, then it'll get a little more basic.
If you put a pH meter like boiling water, like almost frozen water, would you see a difference?
You would have to have a pretty darn accurate pH meter.
Not like what this is.
Maybe. I mean, you could try it out. I don't know the accuracy to which they're gonna work, but yeah. I think if you standardized it to 7 to make sure like 25 degrees Celsius water is 7, then you
Yeah.
might be able to see the difference, yeah. And you probably want to use the same stick. Or
The same type of.
yeah, or the same scale standardized stick, yeah. Okay. Yeah. Yeah, that's just something you'll have to remember. But yeah. Yeah, this one, that's why I didn't want to, that's why I just wanted to go over right away. It's just new information, I guess. Yeah. Alrighty, that's pretty much it for today, guys.